So this is the second part of the A2 chemistry equilibrium videos lessons. So the first part you really need to have covered before you look at this video. The first part deals with KC expressions in terms of just writing them, working out what goes top line, what goes bottom line, and then also working out units from those and working out how changing KC can allow us to work out whether there or not a reaction is endothermic or exothermic, and also whether there are more moles of gas on the left hand side or the right hand side. And we also dealt in the last one just with some Le Chatelier's principle stuff, where we just changed conditions within an equilibrium and we looked at how an equilibrium would respond to those changing conditions. So you may want to go back and review that first video if you're not familiar with that type of stuff before you start this one. So this one deals solely with the calculations. So we're going to start off with some fairly straightforward KC calculations, and then we'll move into some past paper ones, and we'll try and cover all bases in terms of challenge of questions, so from the very simplest ones to ones that are a bit sort of left field and that might throw you. Okay, so a general method for working out KC calculations. So you follow this, and hopefully by the time you've done a few KC calculations, this is pretty much second nature and you just do this automatically. So the first thing you have to do, you've got to write the balanced simple equation. You have no choice. Now, very often in KC calculations and examination papers, you'll be given that. And you use that then to write the KC expression as we did in the previous video. Then, if necessary, and it probably will be necessary to be honest with you, I think it's very, very unlikely that you're going to just be given the concentrations of the reactants and the products in a KC question. You're going to have to do some calculating and some problem solving in order to get those. So anyway, part C, if necessary, calculate the unknown equilibrium concentrations of reactants or products from the initial concentration and the reacting ratios. We're going to do a lot of that in this video because that's where these calculations will sort of orientate around. Then we substitute in all the known values now that we've spent calculating time calculating out in part C. And then we calculate the unknown. Okay, so that might be a concentration or a reactant or a product, or it might be the value of KC. And we'll do questions as we go through this here, which will allow us to do all of that. We'll do once we calculate the amount of reactant that we need, the amount of product that's made, or the value of KC, which is the most common. The last one there is the most common calculation that you will get. Okay, but that's not to say you don't practice the other ones, because the other ones are less common. Okay, they are a bit more difficult, a little bit more maths going on, but you definitely need to practice them. Right, so let's look at a very simple one to get us going. Right, so what's the first thing I as a teacher when I look at this? What am I thinking? Right, well, I'm thinking there's a reacting ratio of 1 to 1 to 1. Okay, so it's a nice simple one, in other words. Okay, then so we write out our equation. I know we've got it up above, but we put it back again. I'll just put that arrow in there. There's a little question mark has popped up in the PowerPoint. That's just where the arrow is. We write our KC expression as per the last video, where we have reactants, products over reactants, and we have them all risen to the stoichiometric powers in the equation. So it's 1, 1, and 1. Of course, we don't write those in, but you can if you want. And then we've got to start taking the information from the question up above to allow us to eventually work out this KC. So let's go up above. First of all, we have an equilibrium of 298 kelvins, not particularly important. 500 cubic centimeters could be important because we'll have to work out concentration, remember, and concentration equals number of moles divided by volume. The volume would be 0.5 because remember that's in decimeters cubed, so we bear that in mind for sure. Okay, we have 500 cc's of methanoic acid solution is found to contain 0.04 moles of, so we'll just write this in, and I would do it this way, ICE, so ice, and then C for final concentration. So initially we have got 0.04 moles of my hydrogen, 0.2 moles of methanoic acid, and we've got to calculate the KC. Okay, so let's have a look at how you go about this. So there's my initial moles, okay, my I, okay. That's my initial concentrations here. Now, you might say, all right, well, we didn't get any information up here about the amount of methanoate ions in here, but how do we work that out? Well, we have 0.2 moles of that to begin with. We made 0.04 moles of this. Okay, so if I go back to my method here, okay, this was plus 0.004 moles. Now these are made, as we said earlier, I said the first thing that I would take when I look at this equation is the ratio. If I make 0.004 moles of hydrogen ions, which it tells me up here, well then the change is positive 0.004 moles of that. So at equilibrium I have 0.004 moles of that, 0.004 moles of the hydrogen ions. So every time 1 mole of hydrogen ions are made, or 1 mole of methanoate ions are made, 1 mole of methanoic acid reacts. So if 0.004 moles of that are made, minus 0.004 moles of that is what is used up. Okay, so I make 1 mole of, or 0.004 moles of this, I've used up the same of that. So my equilibrium mole of my methanoic acid is 0.2 then, okay, minus the amount of moles that have been used up, which is 0.004 of course. That leaves me with 0.196. So at equilibrium I have those number of moles of all of those. Now remember, you've got to put into your equation concentrations. Concentration equals moles. I've got my equilibrium moles divided by volume, so it'll be all of those divided by 0.5. Okay, so or multiplied by 2, either or, doesn't matter. So this one becomes 0.392 and the 1.004 divided by 0.5 becomes 0.008. Okay, and that will of course be the same as the same numbers. So my calculation then becomes Kc, I just do it up here, equals 0.008 squared, because it's just that times that, those are the same numbers, divided by 0.392, I just crunch those numbers now, divided by 0.392 gives me a value of 0.000163, so my Kc, squeeze it in here, is 0.000163. Okay, you then have to of course do your units. So my units on my top line and on bottom line. Top line is moles per dm cubed squared. So multiplied by, I'll just write capital M for that, divided by moles per dm cubed. Cancel that, I bring that divided by 1, just becomes moles per dm cubed. So my units on my Kc, I know it's a bit messy, the unit are way up there. Okay, become mole dm to the minus 3. Okay, so hopefully that makes some sense. It's a bit messy all over the place, but it gets the point across, right? So this is the method that I really apply all the time, and it works well. You'll see it taught differently and by different teachers and different textbooks, but ICE, students remember that well, and then C at the end, we've got to go to concentration. Right, so let's look at the next problem then. Okay, so in this one, we have sulfur dioxide and oxygen going to sulfur trioxide. Now, first thing I notice, 2 to 1 to 2. Okay. Right, next thing then I do is my I, C, A, and C at the end. Okay, so I quickly note there's a volume up here, so it's 20 decimeters cubed. Okay, so 20 dm cubed, that's the volume. So just make a wee note of it. I'm starting off with 2 moles of SO2 to begin with, and I'm starting off with 2 moles of oxygen. 0 moles of that, of course, to begin with. Although sometimes they do put some product in, so just be aware of that, and we probably will meet 1 or 2 like that later on. Okay, it tells us then, at equilibrium we had 0.4 moles of sulfur trioxide. So therefore, that's positive 0.4 moles of that is made. Now let's go and see how much SO2 is reacted. So every time 1 mole of SO2 reacts, 1 mole of SO3 is made. So if I'm making 0.4 moles of that, this is minus 0.4, which means at equilibrium I've got 1.6. Okay, now let's look at the oxygen, because that's not as nice a ratio. 1 mole of oxygen makes 2 moles of SO3. So if I made 0.4 moles of oxygen, that is minus 0.2 moles of that. Okay, so that is 2 minus, that becomes 1.8. Okay, right, then finally my equilibrium is that over 20, that over 20, and that over 20 brings me to concentration. Okay, so let me just crunch those numbers quickly on my calculator. Okay, so those are the numbers then that I get at concentration. I bring them down and I plug them into my Kc expression. Okay, so my Kc expression would have been SO3 squared, concentration of SO3 squared, divided by concentration of SO2 squared, divided by the concentration of the O2. So I just plug those numbers in. Okay, so I've got that .02 squared on the top line, divided by bottom line is 0.08 squared times 0.09, and that gives me a Kc this time of 0.694. Okay, my moles or my units on those moles per decimeter cubed squared will cancel out moles per decimeter cubed squared. So I then have 1 over the moles per decimeter to the minus 3, so that becomes moles to the minus 1 dm to the 3. Okay, let's have a look at the next one. Right, so this time we have changed the goalposts a bit, and that we're using the result from question 2, in other words the Kc of 0.694. Okay, and this time we've got to calculate how many moles of SO3 will exist in equilibrium when you've got 0.4 moles of sulfur dioxide and 1.2 moles of oxygen in a 10 decimeter. So we've got to do some rearranging of the equation. We already know, as we said, the Kc, okay, because it's the same temperature and it's the same reaction as we had in question 2. So the Kc, temperature dependent, doesn't change. We've got to get the concentration of SO2. Okay, so we've got, it tells us up here, we've got 0.4 moles of SO2, moles of SO3 I should say, and we've got 1.2 moles of oxygen. So we just convert those into concentration and plug them into our Kc. Some of you might be able to see how to do this now. You might want to pause the video here and forge on, check that you get the right answer here. Okay, so equals the Kc, which is that value there. We then rearrange it to make SO3 our subject. Very simple. That becomes Kc upon the concentration of SO2 times the concentration of the O2. Okay, is so. Remember, that's the concentration of the SO3 squared. We've got to square root that then. Gives us the concentration of the SO3. Now we're not quite there yet because the question says at the top how many moles. Some students will use this as their final answer, but you remember you have another route to go. Remember, number of moles equals concentration times volume. Okay, so all we're doing in this instance is taking our answer from above, timesing it by 10, and we get that 0.115 moles is our answer. Okay, so we've changed the goalposts a little bit, but not too bad, I don't think. Okay, let's have a look at this one. This time we've got 1 mole of ethanol and ethanoic acid mixed at a fixed temperature, and the reaction mixture at equilibrium is found to contain 0.65 of ethyl ethanoate. We've got to calculate the equilibrium constant, the Kc, with its units. Now, those of you who are on the ball might think, oh, this is easy. Okay, if we just scroll down to the equation, we have a lovely equation here. It's 1 to 1 to 1 to 1 the whole way across. But if you are on the ball, you may notice that there is no volume given. Right, so we do not actually need the volume in this instance. And I'll show you more as we sort of go through it why we don't, but the simple fact of the matter is, if I write out my Kc, Kc is equal to the concentration of each, which is concentration is moles over volume, okay, multiplied by moles over volume for the top line. The bottom line is the same, okay, because they're all risen to the power of 1, yes? Now, we have volume and top line, cancels out volume and bottom line. So in actual fact, when you have the same number of moles on the left and the right hand side of a Kc, or an equation, sorry, you do not need the volume. So don't be scratching around looking for a volume in this instance. You just need to get moles, okay, and do your Kc, moles and top line divided by moles and bottom line. Okay, so let's have a look. We'll do our I, C, E. We don't need the C then at the end this time. Okay, so we're starting off with 1 of that, 1 of that, 0 of that, 0 of that. We are going to make, okay, at equilibrium, 0.65 of this. So remember, we make the water in a 1-to-1 ratio with the ester, so we're going to make 0.65 of that. That means we must have reacted 0.65 of that, and we must have reacted 0.65 of that. Okay, that leaves us with 0.35 of that, 0.35 of that. So hopefully the light is shining here, you can see how easy this is. So this becomes 0.65 squared on the top line, 0.35 squared on the bottom line. Let me just do this, 0.65 squared, okay, divided by 0.35 squared. And that gives me a Kc then of 3.45. Now, there are no units. The number of units on the top line and the bottom line are the same. Moles per dm cubed squared on both. And we usually write no units. Don't leave it blank, guys. If there's no units, write no units. There may well be a mark for that. Okay, so again, one that looked tricky enough, but actually in reality wasn't too bad. Okay, let's look at this one, which is tetrafluoroethene. Alright, decomposing. Now, what am I looking at here? And the first thing I'm going to take from this is we have a slightly nasty ratio. Not too bad, but okay, the moles on the left and the moles on the right aren't the same, so we do have to go down to ICEC concentration at the end. So we've got 1.2 moles of our sample, so 1.2 moles of that is placed in a 20 volume container, so there's our volume, just note it. And equilibrium was reached. When equilibrium was reached, we had 0.3, okay, of that, okay. Now that means that minus 0.9 of that reacted. This is 0 and 0. If minus 0.9 of that reacted, that means I made plus 0.9 of that. Okay, 2 moles of this make 1 mole only of the C2F4, so that means I made positive 0.45. Okay, which is that. Right, remember then, C equals M divided by V, so I've got to take all of these because the moles on the left and right are not the same, and I've got to divide them all by 20. Okay, so 0.3 divided by 20 is 0.15, 0.45 divided by 20, 0.22, 0.0225, okay, 0.015 that is, sorry, and 0.9 divided by 20 gives me 0.045. Plug those into my Kc expression, which would be 0.0225 multiplied by 0.045 squared over 0.015, and that's also squared. Okay, so we'll just do that. We crunch the number. Okay, and that comes out at quite a big Kc of 400. Units are, those will cancel, I end up with moles dm to the minus 3 over 1, so my units are moles dm to the minus 3. Okay, Right, this one then is a little bit different in that now instead of having moles, we've got mass of certain things. Okay, so again, we've got to get our equation, and we notice straight away that it's a nasty little equation. We've a 2 to 1 to 3 excuse me, ratio. But we go about it the same way. I, C, E, and we're going to have to process through to see this time. So we started off with 10 grams of A, okay, so this time we've got to bring in moles equals mass in grams over the atomic mass, or RFM. Okay, so we've got to get moles this way this time. So the first one is 10 divided by 46. So we start off with 0.217 moles of that. Okay, there's our volume up there. We just make a wee note of that. And we end up with 0.5 grams of B, which is an RFM of 18. So we do 0.5 over 18 for B, which is 0.0. Sorry, that should not go there. This is the equilibrium moles, which is 0.027. Okay, now for every 1 mole of B that's made, 3 moles of C are made. So we take that and we multiply it by 3 to give me the moles of C that we'll have at equilibrium, which is 0.083. Okay, for every 1 mole of B that is made, okay, 2 moles of A must have reacted. So 0.027 times 2, that's the moles of A that reacted. So this is minus 0.054. So 0.217 minus that gives me the moles of A that we have at equilibrium, which is 0.163. Right, that's pretty much the hard work done here. Okay, now we've just got to get these all into concentration by simply doing C equals moles divided by volume. Volume being 12. Okay, so we divide everything by 12. When we do that, we get a concentration here of 0.0136. 0.027 divided by 12 is 0.00225, 0.00225, and finally 0.083 divided by 12 gives me 0.006, 0.00692. Okay, I plug these into our KC, gives me 0.00225 times 0.00692, that is to the power of 3, remember, divided by 0.0136, that's to the power of 2. Okay, we crunch our numbers then to get our, okay, and that comes out at 4.4 times 10 to the minus 6. Okay, so that's a really small KC. That equilibrium clearly lies well to the left hand side. Okay, so we've got to work out our units. So we've moles of the dm to the minus 3 squared there, so we can get rid of that and that, and we get rid of one of those. Okay, so that will become moles to the 2 dm to the minus 6 over 1, so our final units become moles to the 2 dm to the minus 6. Okay, so hopefully that is another one that might pop up a little bit different. Okay, so this is one that's again different. Okay, so we'll write this one out. Oh, sorry. So we have a mixture of ethanoic acid, which is CH3COOH, plus we have some ethanol, C2H5OH, and that goes to, I'll just write ethyl ethanoate because it's more hassle. It's worth to write all that out, not necessary. So let's see what we've got. ICE. We don't need the C because remember our moles on the left are equal to moles right in this equation. So we're going to start off with 0.2 moles of that and 0.111 moles of that. And that was allowed to reach equilibrium. Right, the ethanoic acid present required then 54.4 of 2 molar sodium hydroxide to react. Right, so this is what's different about this one. We're taking that whole thing after equilibrium and we are taking our ethanoic acid, just our ethanoic acid, and reacting it with sodium hydroxide in a titration. Okay, now that is the equation for this. The reason why we need this is we need the ratio at which the sodium hydroxide reacts with ethanoic acid. Most of you will know that anyway. I would hope it's 1 to 1 even. Alright, now my number of moles of this, N equals C, which is 2 times 54.4 over 1,000, which is 0.0544. Okay, so let's just do that. 0.0544 times 2. So the moles of sodium hydroxide that reacted were 0.1088. That tells me, therefore, in the ethanoic acid, or the amount of ethanoic acid that was left over at the end, has to be that, because all the ethanoic acid reacts with the sodium hydroxide. That allows me then to fill in this value here, so 0.1088, which then allows me to work out how much of the ethanoic acid actually reacted. So this minus that tells me that this was minus 0.0912. Because they react in a 1 to 1 ratio, if 0.0912 moles of ethanoic acid reacted, the same number of moles of ethanol reacted. Now we started with 0.111 moles of ethanol. Okay, we reacted 0.0912, which meant at the end I will have 0.0198 moles of that. Now, if that number of moles of the reactants reacted, and they react in a 1 to 1 ratio to form products, that will be that, and that will be that. Okay, so therefore plugging these values into my KC, my top line will read 0.0912 squared, my bottom line will be 0.1088 multiplied by 0.0198. Let me just do the numbers there. Squared divided by 0.1088 multiplied by 0.0198. And I get an answer here of 0.181. I'm not getting any answers that are actually on this here. Okay, right, so I've made a mistake here somewhere. Let's go find it. Okay, so those numbers are correct. I must have punched something wrong into my calculator. So if I do those numbers in my calculator, I get the answer C. No units for that one. Okay. Right, this one then again we're back into using mass. So we've got 12 grams of ethanoic acid. You see they've been a little bit sneaky here. They've put ethanoic acid first in the question but second in the equation, so just be a bit cautious of that. So the moles of that will be 0.2, and here we have 9.2. Okay, just check it's the same, divided by 46. Okay, so it is indeed being rather kind to us there, so that's also 0.2 moles. Now, the reason why this one's a little bit different is we've added ethanoic acid, we've added ethanol, but they've also put in at the start, initially, 18 grams of water. 18 grams of water is 1.0 moles of water. So if I do, let me just tidy this up a bit so we can do our ICEC. So ICE, we don't need a DC, that's 0.2, that's 0.2, that's 0 to begin with, but that's 1.0. Okay, if 0.133 moles of ethanoic acid remains, so that means that value there is 0.133. Okay, which means this value here must be the same, 0.133. So my moles of my ethanoic acid and ethanol that reacted was 0.2 minus 0.133. Okay, it's 0.067. So 0.067 moles of that reacted. So this must be 0.067, and this must be 1.067. So we're pretty much home and hose now. We don't need to convert the concentration because the moles on the left are equal to moles on the right. Okay, so 1.067 multiplied by 0.067 multiplied or divided by 1.33 squared. Okay, 1.067 divided by 0.133 squared gives me an answer of 0.04, and remember there are no units because the number of moles on the left hand side equals moles on the right hand side. Okay, another couple to do here, and then hopefully you guys will have gotten on to how to do these. Right, so the concentrations of HF, okay, and F minus are respectively, okay, so HF is 0.0077. What they'll help you do here is you look at that, and then you go from that and you get these mixed up, okay, so just be very methodical about how you go about it. So our Kc is equal to, we have HF of course on the bottom, so that's 0.0077, and our top line for our fluoride ions here is 0.0023, but remember fluoride and hydrogen are in a 1-to-1 ratio, so they will be the same. So my top line will read that 0.0023, okay, divided by 0.0077. Okay, and that gives me 0.000687, so 6.87 10 to the minus 4 in other words. Okay, very straightforward. Which of the following substances when added? So this is a tricky little one. There's no maths involved, but I just thought I'd put it in here. We need to move the equilibrium to the right. Okay, so hydrogen, well, hydrogen gas isn't going to have any effect on that. There's no gases in there. Hydrogen chloride, okay, move it to the right. Well, this is actually what hydrogen chloride is here when it's in water. Hydrogen ions and chloride ions. If I put that in, it'll actually move it to the left. Sodium chloride would produce chloride ions, okay, which would also move it to the left. Sodium hydroxide, well, there isn't even any sodium hydroxide in the reaction equation anywhere, but this is the sneaky thing. Hydrogen ions, as you know, react with basic hydroxide ions to give you water. So by adding hydroxide ions, I am removing hydrogen ions, and that causes the equilibrium to move to the right. So indirectly, the sodium hydroxide causes that equilibrium to shift to the right hand side by removing a product. Okay, what does adding a catalyst have an effect on the rates of the forward and reverse reaction and the position of equilibrium? Right, basically remember that a catalyst doesn't affect the position of equilibrium, so therefore wrong. It increases the rate of the forward reaction, a catalyst, but remember it also increases the rate of the reverse reaction by exactly the same extent. So the answer is D. Right, this one I chose because instead of giving you moles or mass, it gives you percentage of decomposition or percentage of conversion. Right, so we started off with equimolar amounts of hydrogen and oxygen. So equimolar amount just means the same number of moles. So I'll just stick in 1 for that and 1 for that. Okay, at equilibrium 75% of hydrogen by mass was converted. Okay, so 75% of the hydrogen was converted. So let's say, so that is minus 0.75, that's 75% of it getting converted. So I was left at equilibrium with at equilibrium of 0.25. Now, these react in a 1-to-1 ratio, yeah? So that is 0.25. Every mole of those that react give me 2 moles of that, so that's going to become 0.5. Okay, dead simple. So we've got a percentage this time, but that's how you deal with it. So my Kc will become 0.5 squared over 0.25 squared. Okay, remember there's no units because and I don't need the volume because number of moles on the left is equal number of moles on the right. So 0.25 squared. Okay, and that gives me a lovely wee 4. And there is no units. Down here it says calculate the reverse reaction, the Kc for the reverse reaction, sorry, at the same temperature. Well, that's very simple, it just goes the other way. So you would flip that and that if you wanted, or alternatively, it's just 1 over 4, okay, or 0.25, still no units. Okay. Okay, so we have 2 or 3 more to do and then that's us done. And we'll have covered pretty much every base that hopefully the examiner can kind of throw at you, but we will see. Right, So let's have a look. The equilibrium, calculate the equilibrium constant for the reaction. So we had succinic acid is not, so initially we had 0.5 moles of this and we had 0.7. Now that's a bit of an awkward, we'll deal with that in a second, okay? And we were found then to contain 0.18 moles of methanol after equilibrium had been reached. So let's do at equilibrium here, change here. Okay, I don't need volume because the moles on the left is 3 and moles on the right is also 3. So volume isn't given and we don't need it. Okay, so let's say we had at equilibrium 0.18 moles of that left. So we can work out how many moles of that reacted. So that's 0.7. 0.7 minus the 0.18. So the moles of that were minus 0.52. So the moles of water that will be made, because it's the 1-to-1 ratio with the methanol here, okay, the moles of water that will be made would be that. It's a 2-to-1 ratio of methanol to dimethyl fumarate. So the moles of that would be 0.52 divided by 2, which would be 0.26. So 0.26 goes in there. If 0.52 moles of this reacted, well then half of that, so minus 0.26 moles of that, yeah? So 0.5 minus that gives me 0.24, of course, okay? And as I said, we don't need the volume of the container here. So my calculation is 0.52 squared, remember that is 2 moles of water multiplied by 0.26, that's just to the power of 1. On the left hand side I have 0.24 multiplied by 0.18, and that is squared because we have 2 moles of that. So let's just do that, 0.52 squared times 0.26, okay, divided by 0.24 times 0.18 squared. Okay, if I punched everything into my calculator correctly, I'm getting a value of 9.04, and that would be no units. Okay, it says down at the bottom, explain why the volume of the container is not necessary. That's just because the number of moles on the left and the right hand side are the same, so they cancel each other out. Okay, so let's have a look at this question. So this is probably, I would say, the trickiest KC calculation that I've seen them set. Okay, so let's have a look. We've got our ICE. Okay, again, we don't need the volume here. Okay, for the simple fact that the moles on the left hand side equal the moles on the right hand side. Right, so we've got, let's put our information. We're looking at what mass of butane 1-ol is required. So let's take a little question mark there and put mass on it. Okay, to produce 58 grams of butyl ethanoate. This is butyl ethanoate, so we've got to make 58 grams of that. Now that is, if we do the calculation, 0.5 of a mole, and it's, okay, when reacted with 45 grams of ethanoic acid, so we're going to start with 45 grams of that, 45 grams of that over 60, that means that we've got, starting off with, I'll just put it down here actually, 0.75 moles of that to start off with. We're going to make, okay, 0.5 moles of the butyl ethanoate, and we're starting off with 50 cc's of water, and the water, it tells us down here, is a density of 1 gram. So that is 50 grams over 18, tells me that I'm going to start off with 2.78 moles of the water. So I'm going to put 2.78 there. Now during the reaction we're making 0.5 moles of the ester, so that means we must be also additionally making 0.5 moles of the water, and that brings my water up to 3.28 moles. Okay, I'm 0.75 moles of my my ethanoic acid, but that must have reacted 0.5 moles of that to leave me with 0.25 moles of that at equilibrium. Right, okay. Now I want to work out x. I want to work out how many moles of my butane 1-ol I needed to start off with. Okay, and I know then at equilibrium that is x minus 0.5 moles, because that's how many moles of that reacted. Okay, so therefore the moles of the butane 1-ol that react will be exactly the same. Okay, now we've been told therefore, and also been told that my Kc is as so. Now, as I said earlier, we don't need volume to get concentration because the moles on the left are equal to moles on the right. So we'll put this into my Kc expression would read 3 equals 0.5 multiplied by 3.28, that's the top line, divided by 0.25, okay, multiplied by my x minus 0.5. Okay, so that's just my Kc and subbing in everything that I know at the minute into 0.25. Okay, so if I rearrange that, my x minus my 0.5, which is what I want to get here, is equal to 1.64. Okay, that's just the top line, by the way. Okay, 3.2 times 0.5, and then I cross multiply the bottom line, which is 3 then multiplied by 0.25. Okay, and if I do that, that means that equals 2.187. Okay, so if I x therefore is equal to 2.687. Okay, that's the, remember, that's the number of moles of x that I have to have up here. Okay, the RFM of the butane 1-ol is 74, so that times that gives me, I would need to start off with 200 grams of the butane 1-ol. So that's a pretty tricky question. Okay, we have made it to, I hope, the very last question here. Okay, it's about the contact process. Alright, so in this one, let's go again, my Kc expression. Let's pop my Kc expression here. So that is SO3 squared over SO2 squared times O2. Okay. The question tells me that sulfur dioxide at equilibrium, so let's go ICEC here. Okay, so I've got a 20 dm cubed container. At equilibrium, 8 moles of sulfur dioxide, okay, is what I've got. So at equilibrium I have got 8 moles of that, and I have 10 moles of sulfur trioxide at equilibrium, and I've got to calculate the moles of oxygen that are present, so I'll put a wee question mark in there. Okay, right, so let's plug these values into my my Kc, because my Kc is 27.9, I know that. Alright, so my top line for my Kc would equal 10 over 20 squared, so the moles divided by the volume, okay, which is the concentration, divided by 20 squared. My bottom line would read 8 over 20, okay, that's also squared, and that would be upon x divided by 20. I want to find the number of moles of oxygen, I'm going to call those that x. Okay, and all of that, of course, equals 27.9. Okay, now if I solve that, okay, the top line becomes 0.25. Okay, the bottom line then becomes 0.16 upon 0.05 x. Okay, so that's just x over 20. Alright, and that still equals the Kc, of course. Okay, so if we go a little bit further, I go 0.25 is equal to 0.008x. Okay, so I've just solved that. equals 27.9. Yeah, okay. Now I do my cross multiplication. Alright, so I have 0.25 times 1 is 0.25. Okay, is equal to my 27.9 multiplied by my 0.008x. Okay, we're nearly there. My 0.25 therefore is equal to, just solve the brackets above, so that becomes 0.2232x. Okay, therefore if I do that, my x then is 1.12 is equal to my x, sorry, yeah, 1.12 is equal to my, okay, so my 1.12 is what x is, equals, that is x. Okay, how I got that, by the way, 0.25 divided by 0.2232 equals x. Okay, and that is 1.12. Now, just where we need to be careful here, the question said somewhere, no, maybe not, okay, thought it said to give the answer to 2 significant figures, it didn't, okay. So anyway, 2 significant figures, it'll be 1.1 moles of X is what we should have started off with, or 1.1 moles of oxygen. Okay, right, so those last 2 guys are, I guess, the trickiest 2 without a doubt. Okay, so hopefully we worked through some fairly straightforward ones, building up to the most challenging ones. You've got booklets of past paper questions and all the answers to them. I suggest you work your way through those, okay? And all the best.